thank you for coming to this seminar and invitation. I'm particularly happy to speak here in front of all these people in Science of Intelligence Center. This is a place we should discuss something very fundamental, right? And then this is the kind of topic I have been working on in the last 25 years. And today I'm going to talk about, most excited about, sensorized soft robotics. And I think many of you, especially Buzz Lab members, are actually our competitors. Okay? And I'm happy to share our views so that we can actually compete even further in the future. Okay, so that's the main topic and main motivation of my talk over here. So I just want to start with a really, really big picture of where we stand at the moment. This will give us why we need to do this research at this point. And I just want to give you a little bit of introduction of where I'm from, University of Cambridge. And in the last 10 years, I was working in the University of Cambridge, and I was really happy and very easy to it was at the same time very difficult for me to survive over there because of the really rich history there, 800 years of history, and there was Newton, Darwin, Maxwell, and Rutherford, and Alan Turing, and me, right? And how can I compete with these guys? Especially I was the first robotics professors in the 800-year history of Cambridge. So I have to do something over there, and that was the kind of motivation back 10 years ago, right? So that's the kind of landscape I was thinking about, and then just thinking really, really big as Newton, right? So that was the idea I started 10 years ago. So what's the biggest story of robotics at the moment, right? So that's how I started. And we are really in the very special moment in the history of mankind that the robots are coming to our society, right? We have been waiting for this, hundreds and hundreds of years. The robots come to our society, and this is happening right now. This is so exciting things, and the reason why it's happening is the robots became cheaper, easier, and faster. It almost sounds like a McDonald's or something, but it's actually the case, right? Robots was really dramatically cheaper. That opens the door for new applications, and it's so easy to build robots in a matter of days and weeks and months rather than decades, years and decades. And that was a really, really moment that we need to take advantage of. And I'm telling my students in Cambridge that if you're doing robotics, you're doing the right thing. And if you're not doing robotics, it's not too late because it's easy and in the past. So everyone should be doing robotics now, right? There's nothing more exciting than this at the moment. So where are the robots? And the robots are actually everywhere. We just need to be aware that the robots that we know is what we have, but the more and more new kind of robots are coming. And that is actually the real question for us to think about. And looking at this EU Robotics Forum report almost 10 years ago, the robots are expected to go to almost everywhere, not only manufacturing or medical robotics, but logistics, autonomous car. These are kind of things that we know and we talk about. But then we have the wider industrial areas like inspection, construction, agriculture, rescue, healthcare, elderly care, personal service robots, and so on, right? So this is a kind of a very, really exciting. The good news is that robots are expected everywhere, but at the same time, we as engineers is not as easy as this one, right? There are lots of things that we cannot solve. Can anyone think about which one of these industries most difficult or impossible to do? Like out of all this list of industry, which one do you think is the most difficult thing? Yeah?
Health and elderly care.
Healthcare, elderly care, why?
Because you have to be very reliable, and you also have to facilitate sufficient acceptance level in the...
Acceptance level. Yeah, a human needs to accept their robots, yes? Any other ideas? Which one? Yes.
Yeah, on the same similar vein, the personal and service robots, again, because they have to be very reliable and people need to accept them.
Any other opinions? Yes.
Autonomous cars because they're trying really hard.
Those cars, yeah, trying hard. Yeah.
Surgical robotics, because
Surgical robots.
life is at stake here.
Right. Okay. Any other unusual answer? Those are people, the proper engineers thinking that way, right? Yes. But anyway, so, this is actually not easy question, and there's no single correct answer to these questions, right? But this is actually very important questions for all of us, for all of our engineers, especially younger engineers, thinking about what you should work on and what you should not work on, right? If you're working in a company, developing a useful applications next 5 years, you should work on the solved problem. And if you're researchers in university, you should work on something the companies cannot work on. But where is the borderline, right? The borderline is not really clear. Some, easy problem, like manufacturing, is supposed to be easy, but some of them are not easy. And it's a kind of mixture of this, and this is a typical Moravec paradox, right? It's very difficult to say what is easy, what is not easy, and that is the kind of thing we need to think about. But that's a really, really fundamental question that all of us need to think about as a researcher, because that is the kind of deciding point, what you work on and what you not work on. So, and I just want to give you one perspective from my point of view, like what is not possible today and what is the real challenge in robotics, right? And this is what we call robotics 2.0. So, what we know about robotics is robotics 1.0 on the left-hand side. This kind of machines, typically we know what are the benchmarks, right? The task and the environments are defined before they're designed or built. And once we know the benchmark, you can use any kind of engineering methods to optimize everything for all the directions, right? You can make it cheaper, you can make it reliable, you can make it no redundancy and efficient and correct, accurate, right? So entire engineering is built to do robotics 1.0, right? And especially Germans, as well as Japanese engineers, really good at robotics 1.0. Right? Because we are really good at optimizing everything, make it cheaper, make it more accurate, make it faster, make it safer, right? But roboticists in Germany and in Japan in particular are in danger because now new kind of robots are coming with robotics 2.0. And this is something very different from any robot studied in the last 50, 100 years or in engineering, right? These robots, the task and environment unspecified or less specified. And in this case, we don't really know what we're building because unless robot goes to the site and see the real situation, we still don't know what they're gonna do, right? In this case, the robots cannot be optimized, right? And the robots cannot be cheap because we have lots of redundancy in the system. And the robots need to be adaptive and creative and all kind of things. And this is actually ourselves, right? Humans, animals are almost like robotics 2.0. We can do everything, but we are not optimized for anything. And that's the kind of thing we need to really think about as a robotics engineers, and that's what we call the robotics 2.0. And so, what we can do in industry today is mostly robotics 1.0, but we have a very little idea about how we can do robotics 2.0, and that is something we need to think about. The same thing in a little more concrete scenario, right? Left-hand side, we have industry environment, which is robotics 1.0, and on the right-hand side, real-world environment is robotics 2.0. And in the industry environment, we have a high level of predictability and a high level of programmability, meaning that we know exactly what the environment looks like, what's the task look like, and if the task is too difficult, you can change it so that the robot can solve it, and that's the programmability side. If you have a predictability, programmability, the rest is straightforward. It's a standard engineering. We can do very top-down design. We can do algorithmic design. We can have a massive scale design process, and that's what conventional robotics do. But today, we really need to think of the real-world environment. It's a low level of predictability, low level of programmability. In this case, robot need creativity. Sometimes we call it a design for emergence, right? When we build robots, we don't really know what robots should be doing, right? So that's why we need different ways of building, different ways of designing, manufacturing, and everything. Materials is different. And rigid robots are very useful in the industry environment. We rather don't want to have a soft things in industry environment, right? Because soft things is very difficult to predict. It's safer for humans, but it's actually difficult to predict what's going to happen. So that's why rigid interaction is better. Here, software interaction is inevitable because on the one hand, robots don't know what they need to do, but also you need to negotiate with the environment if you actually don't know what they are. Right? So this is a kind of rough landscape of what we think really the challenge of robotics today, and that's what we should be working on as a researcher. Okay, so now the question is the humanoids, right? Every day we look at very impressive videos, YouTube, newspapers, and they do all sort of crazy, incredible things. And in fact, they are really, really good, right? They call this AGI, right? What is this? Artificial General Intelligence. Or humanoids, right? The humanoids robots, they have a human shape because they expect that this robot machine should do something good it can do. And whether this is robotics 2.0 or are we actually having robotics 2.0 or not? How many of you think humanoid robots is the big leap to the robotics 2.0? No? No one? Yeah, good. Couple of them. Why do you think it's a big thing?
You could make like a robot that is like human-like, I think.
Yeah. You think it's different from conventional robots?
Yeah, because I think so, because you know, if you could make like a human-like robot, it would be a huge thing, I think.
Yeah. What do you think? Who was this? Who are you? Yeah.
Like the most difficult challenge.
Most difficult challenge? But do you think now it's happening something different from 5 years ago, 10 years ago?
I don't know if fundamentally.
You don't. Okay. Right. Anyone think that there's something fundamental happening right now? Yeah.
There's more money to be spent.
More money, yeah, that's a good point. Yes, there are tons of money, right, in this field. Okay. I think, yes, there's something really big happening over here, right? The humanoid robots going to the next generation, next phase of robotics. And this is actually, I don't know whether robotics 2.0, but at least it's robotics 1.5 or robotics 1.8 or something like that. There's something significant happening. And from my view, there are two big things happening. One of them is the hardware. Like there's a huge amount of hardware development, motors, sensors, computers. All of these technologies we didn't have 10 years ago, 5 years ago. Now they have it, and that hardware difference can make still rigid and it's still different from humans, but they can do a lot of things because of the hardware. And the second thing is AI, right? The machine learning AI. We didn't have this level of AI 5 years ago, and that is something we should really worry about. And I'm sure this center, Science of Intelligence, they have less emphasis on AI and the rigid robotics. Lots of people work on the soft robotics and so on. But I think we should really think about it carefully because they are very good competitors for us, and they are actually making a huge leap in this area of research. So what is happening over here? I think that's something we should know. And this is a slide borrowed from Rodney Brooks' talk recently. And he is always making a good statement about what's going on at the moment. And he's making a really interesting statement about what AI can and AI cannot do. And this is actually influencing directly what humanoids can and humanoids cannot do. So what AI can do is imitation, generation, memorization, reacting. What AI cannot do is innovation, understanding, reasoning, planning. It's a kind of very ambiguous terms, but I hope you get an idea, right? How many of you have used ChatGPT? Right, so most of you using ChatGPT, right? The ChatGPT is exactly this. They're really, really good at imitation, generation, memorization, reacting, but they have a very limited capability of innovation, understanding, reasoning, and planning. And I think this is the kind of things that we AI researchers are really trying to solve at the moment, right? So today, AI solved the problem of left-hand side, but now going to the right-hand side. So the AI is, in any case, going to the right-hand side directions, no matter what, no matter how successful they're going to be. But this is the direction we're going to go. But I think we, as a soft robotics and embodied intelligence researcher, we should really think about what they're doing, what's the limitations of them, and how can we work with them, or how can we compete with them. And I think it's very important to know what they're thinking about, what their challenges are. So I think this slide is very important to understand where we're generally going with robotics, and that's something I wanted to point out. But now the question is how far we can go toward the right-hand side, right? So that is another really interesting question that some, computer scientists, notable computer scientists like Stuart Russell, he's one of the most well-known computer scientists in Berkeley, and they think that the AGI, artificial general intelligence, can be actually successful, 50-50 at the moment, right? That's what they say. The reason why they can be successful is lots of money, as some of you said, right? 10 times the Manhattan Project they have in the US. And that's an enormous amount of money. So something can happen if you have that much amount of money. And they have many clever people working on it and lots of different kind of ideas. And this is the reason why they might be successful. The success that they mean is that by 2030, how many years left? 5 years left? They're going to do AGI, right? In 4 years, 5 years. And the critical thing is that at this point, right, they're going to have the scaling law that the science or programming or AI research can be done automatically by computers, right? The human researcher is not necessary to do AI research, and then AGI can happen, right? So that's what they talk about. I don't know how realistic it is, but it can be if you have so much money and so much people, and that's the scenario, right? Scenario one. But scenario two is that probably it's not going to happen. At least we believe it's not going to happen, right? I hope. But the idea is that they all rely on one single technology of deep learning, and the deep learning can be dead-end. We don't know. But a more realistic scenario is the running out of the real data, right? The deep learning needs real data, and the real data is probably going to run out in the next few years. Or maybe people just get lost in the AI mega winter. Maybe we just do lost enthusiasm and so on. So this is the kind of landscape we stand at the moment. So this is what AI people are talking about, machine learning people are talking about, and how we as a robotics engineers can think about this situation. And this is the AI story, right? And robotics is a lot more difficult than AI, and we are doing a lot more difficult things than they are doing. So we need to actually think about how to go beyond what they are talking about. Okay, so now I just want to talk a little bit about embodied intelligence here, right? So embodied intelligence, what we mean is that we think about body, right? If you think about information processing somewhere happening in cyberspace and that interact with the real world environment, and usually computer scientists don't think about this, or at least they can think about the information processing with the minimum influence by the embodied interactions, body interactions. And that is a very, very successful way of doing this, right? If you don't worry about embodiment, you can do very scalable things, very scalable computation, scalable cyberspace construction. But we think, actually this is very important. The intelligent system need a body, and the intelligent system need to take advantage of body, right? So that's a kind of two-way of looking at this. And I'm, for some reasons, happen to stand in the embodied intelligence side. So the information processing cannot be independent from embodied interactions. So So what that means is the basic information processing should be structured through embodied interaction. Right? So if you have a body interacting with the world, that should influence the way how the information processing should happen. So that is the kind of our idea of how information embodied intelligence is in the relationship with the information processing. So from our point of view, only way we can compete or contribute to AI research is how we can structure the physical body for better information processing. And that is something I want to discuss with you in the rest of my presentation. So in this framework, I think that the information processing happening in embodied interaction is a very important thing. And that's why we talk about the morphological computation. So it's almost 20 years ago, we started talking about this. At the beginning, we didn't really define it very well, or we didn't define it on purpose because we didn't know what we were talking about. But the morphological computation is roughly something to do with the physical processes and the information processes. Doesn't matter it's a computer or controller or brain, but something to do with physics and the information processes. And in other words, it's something to do with the body, brain, and the environment. This is the title of this seminar. What's the title of this seminar?
It's,
Mind,
body, and
Mind, body, and they're almost the same, right? So I'm happy about this. That's why I wanted to introduce this. So in 2020 years ago, we talked about this, and then I think this is a kind of an interesting starting point of our exploration. So last 20 years, we talk about the morphological computation in many different ways. And we struggle at the beginning, well, we're still struggling today, but I think we're getting better understanding because of this 20 years of research. So what is morphological computation, right? The morphological computation is nothing like this, right? If you talk about computation, nowadays computation is just, big neural network. The important things about the conventional computation, informational computation, is the computing system that talk about the relationship between information input and the information output. It's all about the information, right? There is no physical things in between or outside of it, right? They are not interested in that. But morphological computation, the difference is that we think about the physical input and physical output, right? So that's the fundamental difference. And as soon as you think about physical input, physical output, and some non-trivial relationship between them, it becomes really interesting questions that we don't have to follow. For example, the Shannon's definition of information theory, or Markov decision process, or Turing machine structure, and so on, right? We can really freely thinking about any relationship, physical input, physical output, without computational restriction, the conventional computational restriction. So that was the kind of idea of this morphological computation. And then roughly, I've been thinking about the three different types of a morphological computation. I call this type 1, type 2, type 3, and I just want to introduce what is mean by morphological computation from that point of view. So the type 1 morphological computation is about replacing or simplifying control. So the easiest example is basically PD control. Usually you have a PD control doing this equation, PD equation, and using sensors, controllers, and actuators, and so on, right? But you can actually replace this controller with the exact same controller with the spring and damper, mechanical spring and damper system. And that is the kind of simplest example how we can do morphological computation for the purpose of control, right? And the exact same similar idea can be applied to passive dynamic walker or universal gripper. Basically, you can do the control of walking like a humanoid robot, but you can do the exact same thing for the mechanical system. I don't think I need to explain this, right? Because everyone knows. So we have a purely mechanical structure that can walk down the slope, converting potential energy to kinetic energy, right? But this is not just a simple a mechanical structure. It has a very intelligent control over here, right? Because this one is not just a ball rolling the slope, but it has a feedback control mechanism embedded in mechanical structure, right? If you perturb it a little bit, it can come back automatically for the nominal trajectory or stable locomotion process. So this is, in a way, similar to how we can make intelligent feedback control into the mechanical system. And that's one example of morphological computation. And the similar things for the universal gripper, right? Yeah, I think everyone knows that we have this balloon filled with the particles, and if you inflate it, you can change the shape, and that's why you can change the shape of the balloon to the object physically in contact with, and then exert a vacuum, and then you can give pressure. Does anyone know what is the morphological computation in this balloon? Like, how can you explain what's the intelligence, what's the computation in this universal gripper? What's the controller? What's the intelligence in this? Yeah?
I think a gripper automatically adapts to the object.
Adapt to the object? Okay.
Yeah, compliance.
Compliance? Okay.
It maximizes the friction surface with the object.
The friction surface of the object. Okay, I think it's getting better and better, right? But this one is actually very well explained in this paper at the beginning. I really like this paper very much because they explain what's a morphological computation in it, right? Morphological computation in this robot can be actually written down in equation, right? And if you look at this paper, they give these equations really nicely, that the gripping force of this robot, Fh is equals to sucking force time plus the friction force. So there are two components in it. And then this friction force and sucking force can be calculated if the object is like this shape, right? So this shape is basically a sphere shape in 2D cross-section of it. And you have to parameterize it, and then you can actually write down the equations of how much force happening between the object and the gripper. And this is the morphological computation, right? All of these equations are happening without robot knowing it, but the mechanical system can make this equation. So I'm talking about the friction force, as you said, is the friction is the function of radius of the object, and then the coefficient of friction, and the angle, the size of the ball, and so on, right? And then so these equations are actually coming automatically just by having shape of the object, shape of the gripper, and then all of suddenly this actually happens. And again, this is a kind of feedback mechanism. If you have a different size object, and then this force changes automatically, right, without the robot knowing it. And that's actually morphological computation. We can actually write down all these equations by knowing all the physical processes. So that is the kind of examples of how morphological computation can be implemented into the as a controller of robots, and that's a type 1 morphological computation. And then the type 2 morphological computation I want to talk about is what we call the sensor morphology, like how morphology can filter, amplify, and convert sensor signals. And that is the kind of example that's shown in the insect face-set eyes, or whiskers of rodents or cats, or even humans use our hands, the shape, to amplify or modify the sensor signals through interactions, right? So that's a type 2 morphological computation. And I just want to give you one crazy example, which is my favorite example, which is not very well cited so far, but this is one of my masterpiece project about how robot can visually detecting force and temperature through morphology, right? So in this video, it's showing the robot that is able to a bit of a 3D printing manufacturing. So end effector has the nozzles with the thermoplastic injection, and then with this manufacturing methods, robots can make a whisker out of the thermoplastics, and you can actually see the deformation of whisker by using the camera in the back of the robot. And then depending on the shape of the whisker, the robot can detect different kind of forces interacting with the environment. And then for the temperature, you can actually, this is thermoplastic material, right? So thermoplastic can melt down if it's hot things attached to it. So that's why the robots structure this mechanism. And if it's touching a hot thing, this thermoplastic fall down. And if it's not hot, it's going to stay there, right? So in this way, the camera can detect how hot it is by looking at the interaction of this object. So there are lots and lots of mechanism built in the system, but what I want to show you is again the morphological computation of the sensor, right? So what's really important is the structure of whisker gives the sense of interaction with the environment. So if you think about the elastic beam interacting with the rigid thing, you can bend the structure with the interactions, but the question is how much bending is going to happen. Right? So what actually the morphological computation happening in this structure can be written down in beam theory. I don't want to talk about the mechanical engineering details of this, but this equation actually tells how much bending is going to happen depending on the structure of the whisker as well as the force exerted to it, right? So if you can change the mechanical shape of this whiskers, you can actually change what you can sense, what you cannot sense. And this diagram actually shows the thickness of the whisker with respect to sensitivity and the sensing range. So if you have a thick whisker, you can measure larger force. Thinner structure, you can measure more small difference in the force. So just by changing the structure of sensor, you can measure different kind of interactions, and that's the equations explaining what the morphological computation over here is. And then the same thing for the temperature thing, right? So this is thermoplastic material. It's reactive to certain temperature at once, but again, we can write down equations how the melting process of the structure happens, right? I'm not going to go into details, but the idea is that actually the touching point of the thermoplastic is very important. If it's big, you can sense the larger temperature, and if it's small, you can measure the smaller difference in the temperature, right? So the sensitivity and sensing range is also dependent on the structure of the sensor morphologies. Again, this is another example of a morphological computation. And then the sensor morphology question applies to actually the tasting problem these days, and how the information and the sensor can be enhanced by using the physical interactions. And in this examples, we built actually cooking robots that can taste food. And we started this cooking robots project a while ago, and lots and lots of cooking robots around the world, but none of the cooking robots can actually taste any food. So that's why we started thinking about how the robot can taste any food. And the starting point was this, one of my PhD students, Greg Sohatsky, started thinking about the tomato scrambled egg, whether a robot can actually discriminate 9 different dishes of the tomato scrambled eggs. Lots of tomatoes, no tomatoes, middle tomato, lots of salts, no salts, and medium salts, right? And how the robot can discriminate this in 9 tastes of scrambled egg. And this is not an easy thing. And AI cannot do this today because this is not only visual information, right? This is multimodal sensory information necessary. So, so what we did, I'm not going to go into the details, but what we did is not only compute the visual information used in this research, but we put some salinity sensor over here. This is basically the sensor that measures the saltiness, but the salinity sensor is nothing more than the electrodes measuring electrical impedance in between, right? If you have a salty food, you have more impedance, less salty foods, less impedance, and that's something like that. But if you can see the relationship between the visual image and the taste map. So taste map is just basically dipping the sensors hundreds times into the dish and then measure the impedance across the dish. Then you can actually see the nice correlation between the ingredient of the food and also the distribution of the impedance across the dish. So that's the one thing, and we try to discriminate 9 different dishes, the taste of it, by using this information. But actually, the success rate is not very high, so this is just an F1 score of discriminating, classifying the 9 different dishes. And the success rate is almost like 75% or something. If we just make a mix and then get the homogenized samples, the success rate is like a 55%. So we're not very happy, and we're thinking about what else we can do. And one very clever idea that Greg found is that chewing is very important, right? If you taste food, you have to eat it. You have to really masticate it. And that process actually improved the information content of classification much, much larger. So what he did is basically putting this as scrambled egg in the mixer and then just mix them around and then do the same thing. And how much sensor information distribution changes depending on the mixing level of the food. And then in the end, he got a 95% success rate in discriminating 9 different dishes. So this is actually one example, right? What AI can do and what AI cannot do. AI is heavily dependent on the visual information and the language information. But just adding additional sensor information as well as active interactions with the object, and you can actually much better performance discriminating different elements. So that's a kind of ideas how we can apply the robotic morphological computation for the purpose of sensing. Okay, so this was an example of type 2 morphological computation. And then the third one, so the type 3 morphological computation is actually programming the behavior with morphology, right? How can we control the behavior of a robot by changing the shape or morphology? And that is the question we're also working on very hard. And there's lots of examples of this kind. I just want to introduce some of our projects. And one of my favorite projects is this self-excited vibration robot. So I gave elastic beam to my students, and then they just bend in this beam in different ways to make this robot do some locomotion, right? So basically, all of these robots made out of a beam, elastic beam, attached to some rotating eccentric mass. And how can they think about the solution to make this robot moving forward just by changing the shape of an elastic beam? And there are many, many different kind of solutions, right? There's hopping robots, running robots, or walking robots. And this is using exactly the same mechanism, but using basically the shape of the robots to do different kind of locomotion. So this is a kind of human-based evolutionary process of a morphology, but then we actually automating this kind of a morphology exploration by ourselves. And one of the projects we have been doing is the folding paper experiment. This is a kind of easy way to explore morphology a little better. So this is an idea of how we can shape the piece of paper by using laser cutter, and then depending on the shape of the paper, the paper can fall in different ways, right? So this is a kind of easy way to demonstrate how the shape influence the way how the robots behave. And this is actually a very famous experiment started by James Maxwell in the 19th century, that they discovered basically 4 different species of a folding pattern of a piece of paper, right? When you drop the paper, it falls in one of these 4 different ways. And this is an example of how you can control the behavior of the shape of paper, right? But actually, there are many, many, many different kind of species of the folding style. And that is one of the projects we did about 5 years ago. So the Maxwell actually did a lot of research about the disc shape of the paper, but one of my students, Toby Howison, found a V-shaped paper is a lot more interesting, so that's why he started exploring it. So V-shaped paper have only 2 parameters, the length of wing and the angle of the wings, right? So only two parameters, but just by changing these two parameters, this paper can fall in a different way. There are 4 different ways, right? So this is the helicopter falling, and then we have what is this? Asymmetric spinning. So this is like falling down like this. And then there are 2 other falling pattern like promenting, and it's going to come back again. Let's see. Start over. Yes. So, and the promenting is falling just going straight like this. If you have a shorter leg, the wing length, and this undulating is like swimming when you have a longer wings and so on. So depending on the parameter setting of these 2 parameters, right, the length and the angle, then you can actually almost always determine which falling pattern is going to happen. And that's a really, really interesting thing because the shape of the paper determines many different ways of falling. But this is not only the thing that we found interesting. If you look at this more carefully, it's not just one-to-one mapping of the paper shape and the behavior, but it's actually transition. If you look at the transition between the falling patterns, then you can almost find something like a Markov decision process between the behavior patterns. So depending on the shape of the paper, but also depending on the initial condition of the falling position, then you can trigger different kind of Markov decision process. And that is the kind of starting point of how we can think about non-trivial morphological computation, right? We can actually program the pattern formation by changing the shape and the position of the robots. And that's the kind of starting point of how we can start thinking about more complex behavior programming by manipulating morphology. And that was the kind of the main idea of this experiment. So I hope you get an idea of what morphological computation. This is more or less what we did for the last 20 years, and there are many, many examples like this. And lots of people say, okay, so what? How can we compete with? What's the relationship with conventional computing? What's the relationship with AI and so on? But I think we are now getting to a really, really exciting point of how we can scale up this morphological computation and embodied intelligence in a more systematic and a bigger impact. And one of the really exciting things we are doing at the moment is the theory for embodied intelligence by using reservoir computing framework. How many of you know reservoir computing? No one? Almost no one? Okay. So this is becoming a really big thing. And maybe you can learn something from my lecture today. And the reservoir computing seems to be a really interesting framework about how we can think about embodied intelligence more systematically, right? So especially for computer scientists, this is the easy way to understand what embodied intelligence is. So the reservoir computing started with computational reservoir computing, which is shown in this diagram. And the reservoir computing is nothing more than just a recurrent neural network, right? So actually, are you all computer scientists? Yeah, who is not computer scientist here? A few, okay. What's your background?
I'm a political scientist.
Okay. Okay, so you might not know, do you know neural network? Hope, a little bit. Right. So recurrent neural network, we have a bunch of nodes and that are connected with the weights, right? And you can do input-output relationship. And recurrent neural network is a very powerful framework that can do any kind of computation, the conventional informational computation, right? And the recurrent neural network is a very good thing. And the reservoir computing, what reservoir computing think about is basically don't touch the main part of the recurrent neural network, but only touch one last layer of neural network, right? And this is basically enough. And one of the real challenge of neural network is that you have to change the weights of a big network like this And that part, you need lots of computational resources, lots of energy, and so on. And that's the cause of all the problems they have. So that's why let's not touch it. Let's assume that we have a very good reservoir, the network already there, and all you touch is just one last layer, right? And then in this way, you can simplify a lot of things, right? And that's the idea of a conventional reservoir computing, and that was proven to be a very, very successful approach if you have a very good reservoir, right? If you have an infinite complex reservoir, you can actually do any computation just by adjusting the final layer of a neural network. And that kind of intuitively understandable, right? If you have a very good reservoir, it's going to be very useful. You can do pretty much everything that the recurrent neural network can do. But this framework turns out to be a very, very useful thing for roboticists because usually this part is really difficult, and we can actually replace this part with the physical system and physical devices. And if you think about it, lots of physical things, it's very difficult to change, but it already have a rich dynamics inside the physical system. And that's why we can actually use it for the understanding of the physical embodied intelligence. So what we can do is basically take a physical body as a computational device, right? And then just take just one last layer to do the learning, and then you can use the entire body in the computation process, right? So that's the idea of a physical reservoir computing. And that is kind of a really new thing that we can explore. And lots of researchers are looking at this as a new way of thinking about embodied intelligence. And we also have started this the experiment in the last couple of years. So what we are doing at the moment is very, very simple system, right? So that we understand it. So what we are doing is basically the physical system, right? So this is basically a pendulum, like a two double pendula used as a physical reservoir. This is the basically computational system. And then we have some target robots over here, which is a pendulum, right? So but this is an under-actuated pendulum, and this is actually very difficult to control if the torque is limited. So now the question is how this robot can take advantage of this robot, so this is a reservoir, to do the control cycle of this. So this is the brain, this is the robot, and that is something we want to do. And one only thing this robot needs to do is basically tuning the last layer of a reservoir to control the complex behavior of the robots, right? So here's the experiment we did. It's kind of difficult to see, but here's the real robot with the two pendulum. And this is physical robots, right? We have servo motors and a tracking system over here. And this is a simulated under-actuated robot. And if you are a usual robotics engineer, you actually try to control the physical robots with a simulated brain or controller, but we do the exact opposite, right? We do the computation in the physical robot to control the simulated robots over there, right? So that's the idea how we did it. So what we basically did is using this, the learning of the coupling in between, and then you can actually do the physical motion pendulum, trying to control the robot on the left-hand side to swing up, right? At the beginning, it's very difficult because you need to do the under-actuated control, but then you disturb it. The simulated one is also disturbed, and that's why it is trying to recover from it. And if you disturb it stronger, it's going to fall down, and this is the kind of proof that they are actually doing all together, right? So this is actually the physical brain that's trying to control that one, the simulated robots, and that is the kind of a framework we can really think about. And this is a really interesting thing, is because this is actually the real how the physical process can be converted into the control of physical robots, and that is the new way thinking about the computational framework embodied system. And then, so this comes to kind of new ideas of how we can actually do more and more informatization of embodiment, right? And how we can use physical systems into intelligent computational machines and use it for controller purpose. And that is the kind of last part I want to talk about in this presentation. How much time do we have?
So, I mean, the recommendation is to take 60 minutes for the lecture, so we have like about 7 minutes, but it's up to you.
Okay, right. Okay, so yeah, well, I think, I hope you get an idea of how the morphological computation and embodied intelligence comes together, right? We want to have somehow mechanical body used as a computation process, and this is something I really want to discuss at the end of the presentation. So what we are thinking about is our body is not just a body, like the entire body is actually sensors and a computational device. And that's something we want to do in the next step. So what we are doing at the moment is how we can make materials sensors and how we can do materials a computational device. And one of the most exciting projects we do is called electrical impedance tomography based sensor system. So the idea here is that we have some soft materials over here. This is electrically conductive materials, and that can be connected to an array of electrodes. And these electrodes can actually measure the electrical characteristics inside the soft body. And what we can do here is that what electronics can do is basically injecting electrical current through two electrodes, and then you can create the electrical field, and then you can read out the electrical field with the other pair of the electrodes. And in this way, the computer can see what's actually going on in this material. So if you look at this video, on the right-hand side, what this is doing is basically a robot is pushing this membrane, and then the computer can reproduce what's going on in the electrical field in this materials, right? So this is an idea of how we can actually make informatization of the materials, and that is actually really, really exciting things we are doing. So what's important here is obviously materials, right? So we need to have some sort of electrically conductive materials, and that is the kind of baseline of all the arguments over here. So we want to make it electrically conductive, but at the same time, we want to keep it, soft and keep it manufacturable, and keep it stable, and all of these things. Actually, there are lots of know-how in material composition. But if you have materials like this, we can use these materials as for the informatized embodiment. And what we are really pushing full speed in our group is the multimodal tactile sensor processing based on EIT. And the idea is that we can increase the number of electrodes. We started with 8, but now it's 32 electrodes. And if you have a 32 electrode, this is a combinatory explosion, right? We can go up to 1.7 million channels across this 10 centimeter membrane materials. And then depending on the material properties, we can sense different kind of things. We can sense temperature, humidity, touch, multi-touch, and so on and so forth. And then that can be actually extracted from the large number of sensor channels. So the number is really important, right? 1.7 billion channels. It's almost like a camera with megapixels, right? But the question is how much information we can squeeze in to this a lot of information of the materials. And actually, this is the paper which was published yesterday in Science Robotics. And we are really excited to push this together with the ARIA funding mechanism in UK, that we're trying to make it more widely accessible in open access, open source fashion. So if any of you interested in using this kind of framework, I'm happy to collaborate based on this kind of projects. And what we're doing here is basically having different manufactured materials, and they'll make a robotic hand like this. So what's really good at is that we have electrodes implemented only the end of the materials, and the entire hand can be sensor. So we have 32 electrodes in the wrist, but the rest of the hand is completely free for the interacting with the environment. So based on this, we have actually the experiments in how we can make the entire hand as a sensor rather than embedding sensor one by one in a small space. And that's the technologies we are using in this research. Okay, so I think one of the really interesting things is that we really want to go into more and more complex robots in the future. And one of the really exciting thing about bio-inspired robotics is that dealing with the complex nature of a human body. So if you look at the human body, we have about 10 to the 13 cells, right? It's a lot of cells. Compared to the robots we can build. The largest robot we can build is A380, which has only million components, right? Compared to human body, we have million components, right? So our body is a million times more complex than A380. So how can we deal with such a complex problems? And that's what we want to think about. And building such a system sounds like a really crazy thing. But we can learn from nature, right? How we should do such a thing. And one of the really ideas is that the animal grow over time. So our body is never be static. Our body always changes. And we start with one cell growing over this big complex systems. And another important thing is that, we tend to think about the brain is a very important thing, but it's actually a very small part of the entire body. We have only 60 billion neurons in our body, right? Compared to millions of the cells that we have in the body. So why not we using the rest of the body for the complex process of the computation process happening in our body. So what we really need to do next is a really exponential scale up of complexity from what we can do today in the conventional robot building approach to a really biological, bio-inspired approach, going really complex structure. And now our robots have maybe thousands or millions parts, but we have to make it a million times more complex. And that sounds like really crazy ideas, but it's not actually too complex, right? Too crazy, because what happened in the LSI technologies, right? In the last 40 years, this is actually exponential growth in the complexity. So we can actually make this happen in the physical robots to make more so that's the idea of how we can make our embodiment more informatized, and then we can use it as a computation process, and that's the next direction we should go. And the idea is really, how we can do the exponential increase of the complexity in hardware, and that is something we want to we're exploring in our group at the moment, and hopefully we can have a very good collaborations and competitions in this kind of research area. Okay, so I think that comes to the end of my presentation, and I just want to introduce our efforts of putting embodied intelligence researcher together. And this year we had the 5th times international virtual conference. I don't know how any one of you attended this workshop. Some of you? Oh, great. So if you haven't, please do think about joining this, because this was actually very successful initiative. Every year we have about 120, 130 speakers all over the world, top researchers in March and April time. And this is for free to attend. It's a virtual conference. So, you can hop in, hop out, and we are now officially making a partnership with Science, Robotics, and nature machine intelligence to really pushing this direction of research in the future. And this is a place where we can really discuss fundamental research through the international collaborations. So we will do it again next year, probably the third week of March again. But all of these talks in the last 5 years are in the website and all recorded, and you can access to all the talks over there. So please have a look, and you're welcome to join next year as well. Okay, and obviously all of these things happen without all the students and the funding agencies, and yeah, my group became really big as your groups. But I think I just want to acknowledge all of the excellent students in Cambridge and also Zurich, and all the industry partners we have for this project. And I'd like to open for the question. Thank you very much for the attention.